So we're going to start out second semester talking about some alkene reactivity, and in particular alkene addition reactions. And because we've already done that in first semester, what we're going to do is look at our conjugated pi systems, or our conjugated alkenes. And what we should have seen or will see in lecture shortly is that we can kind of activate our pi systems to react in different ways. So our two most common ways that we could activate the alkene to react would be to react them with acids or to react them via radicals. And so both of these circumstances are ultimately trying to affect our pi bond. Our pi bond on its own is not particularly reactive. I mean, we have those p energy or p orbitals with those higher energy electrons, but we really want to kind of get them moving and get them moving out towards something. And to do that, we really have to polarize that bond, which is the problem because we have carbon-carbon bonds, so that's not very polar. So the first thing that we could go through and do is force those electrons to react with an acid. So acids are very, very polar, give us this very strong H+, so the electrons can immediately go out, react with the H+, and we've now formed a carbocation intermediate. Okay, so this is one of our big differences here, is that now we have to reevaluate our problem. And now our problem is not looking at an alkene anymore, but now looking at the stability of a carbocation. So we can again evaluate our stability. It's a positive charge. We need to stabilize that. And we now have a couple options. We can either look within the structure to stabilize that positive, or we can look outside it. In the case of our conjugated pi systems, unfortunately, we have to look in both locations, which leads us to our favorite concept of resonance. So when we're looking at our resonance effect here, we now have those two being in resonance with each other, which means that bromide ion can either come in and react with either of those, producing two different products. And which product we get is going to be dependent on the rest of our reaction conditions, whether we get a thermodynamic product or a kinetic product, which again we'll talk about more in lecture. The other option is going through and activating via radicals. So the same general idea. We've decided that our alkene is not reactive enough on its own, so we throw in radicals. Radicals mess with everything and launch the whole system into a higher energy reactive state. And so through a sequence of reactions, we can end up generating a radical, or a tertiary radical, that can then react with a bromide radical and do an addition reaction opposite the way we would have normally expected, by putting the bromine on the most substituted carbon as opposed to the least. Okay, and we saw that in our primary result up top. Okay, so it's kind of neat, putting it in a different spot. The other thing that can be kind of interesting with this is that we could get rid of HBr altogether. So if you notice in the next reaction down, I've removed HBr, but I've still left the radical initiator. So the radical initiator will then react with the next most reactive thing, in this case our alkene, again forming our radical, which can then react with a second molecule of our alkene, and we end up with a new product. That new product is also radical, and then this can go through and polymerize again and again and again. So we get these big, long, extended alkyl chains. So our radicals tend to push either these non-standard products or non-predicted, non-expected products, and then polymers. So both of these rely on altering the pi bond, so that when we're looking at how our alkene reacts, what we're doing is really focus solely on that pi bond and saying, I need to change that. Okay? But what does our pi bond react with? Okay? Can we change the reacting species? Or can we push it further? Can we change the dynamics, or how our molecules move? Okay, so if we evaluate those, do we get different results? Well, if we change the reacting species, the first thing we need to think about is, well, what's going on? How is our alkene reacting? Well, our alkene is primarily an electron source. And in our previous slides, we said that the electron source wasn't super reactive, so we threw in some really strong acids or radicals to force it to react. Okay. The other option is that we could throw in an electrophile. Okay, so So we can throw in big electrophiles to go ahead and force our reaction to go ahead and push through. And in the first semester, we've seen a sequence of those reactions as well. We've got a nice big spider diagram showing those, and we'll talk about those in a little bit more depth in lecture. Okay, so we could affect the reacting species. If we go back to our conjugated pi systems and take this a step further, okay, notice here we're looking at a radical situation again, but now we're bringing in this question of dynamics. What we want to do is think about what can happen with this reaction. How do our species move, and how do they potentially align with each other? So go ahead and take a second here on your own, come up with some possible products that could come out of this. And I'll come back in a couple seconds after you pause the video now. Okay, we're going to say you're done pausing. So we've got our situation here with our radicals. Our radical could go ahead and force our alkenes to react, and we could end up forming a nice long chain for a radical situation. Okay, just as we did before, and we could even call this group an R group and have it kind of hanging off of our chain all the way down. So if we went through and looked at these and colored these as the individual monomers, there's 1, red is 2, and our green is our third one. So we've, just in case you missed that, we've polymerized outwards in this fashion. If we want to get a little bit more specific and draw in what those R groups are, no pun intended, we have 1, 2, 3, 4. Okay, so there's one possible polymer, and this could continue on outwards, either direction, on kind of indefinitely, as far as we're concerned. Well, some of you, while in the process of putting this together, may have noticed that we still have alkenes that could potentially react, and you are absolutely right. What can now happen is that these alkenes can potentially cross-link out and form more polymers, okay, and more polymer, and more polymer, all the way out, and so on and so on. So we end up with this massive cross-linked nasty mess of polymers, and that's a big deal to deal with, but if we were moving into polymer chemistry, we might intentionally incorporate molecules such as this to force that cross-linking of those polymers, because we now have this big, massive, extensive system that is all linked to itself, much like, say, concrete. So we can actually build a stronger, more rigid polymer by increasing the amount of cross-linkings that occur. So it's kind of a neat little process with our polymer chemistry. So the next concept we could throw in here is, well, what happens if we just get rid of the radical initiator? Okay, could this reaction still theoretically continue? This again comes back to the movement and alignment. When we're talking about movement, we could look at the movement of electrons. Well, one of the things that's nice with our conjugated diene is we do have resonance. Okay, and this resonance is going to be particularly useful for us because now what do we have? We now have this charged species which could then go out and react with our other monomer unit. And we could potentially build a different polymer, okay, or a slightly different pattern. We didn't need the radical initiator to force this reaction to occur. Temperature would be just enough. Okay, heat would be enough to get this thing to go and actually start moving. Okay, so that kind of addresses some of that, or some of the question here, our movement and alignment. But is there yet another way that we could go through and look at this? Okay. The pi bond, as hopefully you remember, can't rotate. So the atoms that are located on the outside of that cannot rotate relative to each other. Well, in that molecule it didn't really matter because it's all hydrogen. But what happens on this molecule? Okay. I can't rotate about that pi bond. So this hydrogen and this carbon will always be next to each other. But is there another bond that I could rotate? hopefully you see I could rotate about that bond. What happens if I do that rotation? What you should see is we end up with this conformation. That gets tricky. That gets tricky because now what happens when I try and go through my polymerization? I have the potential of having those two molecules react with only each other, no other reaction occurs, and what I end up with is a cyclic structure with one pi bond remaining. That may seem a little bit far-fetched, like, oh crazy, that would never happen. Well, we might think that. Turns out, it does happen. And it happened frequently enough that it was named the Diels-Alder reaction, for the guy that discovered this happened, or how this happened. And he went through and named things accordingly. So our molecule with two alkenes is referred to as the diene, because it has two double bonds. We also have the Dienophile, meaning the molecule that likes dienes. Okay, so those are our combinations or the names that we'll reference within this. Before we push this too much further, let's break it down to as simple as we can, which is what you should be doing with every reaction you encounter. What changes actually occur within this? What bonds were broken? What bonds were formed? So if we go through and actually color in the bonds that were broken, we actually lost a pi bond, lost a pi bond, lost a pi bond. We lost a lot of stuff in this. 3 different things were broken. And as far as what was formed, well, we gained that sigma bond, gained that sigma bond, and we gained that pi bond. So that's a lot of different things happening. And if you think back to how we looked at our substitution reactions in first semester, we looked at what things occurred and how those things occurred and when they occurred. And in those cases, it was only 2 things. We broke a bond, we made a bond. We now have 6 different things happening. The order in which those 6 different things could happen could be very, very dicey in that processing. Okay, and trying to decide which happened first, which happened second, all of that fun stuff, all the way up to 6th. But I want you to kind of think outside the box and say, well, really, how much of these bonds broken and formed actually happened? Because if I take a look at that diene, I could just as easily have drawn the structure like this. Oops, I want to adjust that for a second. Well, how did I do that? I took the pi electrons and I moved them there. I took those pi electrons and I moved them there. By showing a resonance structure, I have now removed 2 things from breaking in the course of the reaction, because the relationship between the new structure I've drawn and the old one is identical because they're resonance. Okay? Take it a step further, I can also remove the formation of that new pi bond, because in my structure, or my new structure, it's already drawn. Well, what about the dienophile? Well, the dienophile, I can do the exact same thing. I can draw a resonance structure where I've taken those pi electrons and I've put them on that single carbon. So now what I'm saying is that, well, I didn't really break that pi bond. So now when I go through and look at what changes occurred in my overall reaction, what changes occurred? Well, nothing was really broken, but I formed 2 sigma bonds. So really the only things that have happened, 2 things. I formed a sigma 1, which we'll reference for the rest of this, and a sigma 2. That's it. So now we can think of it just like we did with our substitution. In substitution, we broke 1 bond, we formed 1. Here we're forming 2 sigma bonds. Which happens first, or do they happen simultaneously? Just like SN1 and SN2. Okay, so this is now how our reaction occurs. So the next, or the last part, is a when. Okay, do we get our sigma 1 first, then our sigma 2? Do we get sigma 2, then sigma 1, or do they all happen at the same time? So we get 3 options, the exact same 3 options that we got when dealing with substitution reactions. Well, in this case, you should notice that our sigma 1 and our sigma 2 bonds are identical to each other. So if we say sigma 2 happened before sigma 1, that's the exact same thing as saying sigma 1 happened before sigma 2 because we have a symmetric molecule. So really we are only down to now two options, which we'll call DA1 for Diels-Alder type 1 mechanism. We make the sigma 1, then the sigma 2. Okay? Or the DA2 type reaction, in which case we make sigma 1 and sigma 2 at the exact same instant. You'll notice that I am mimicking the numerical system that we established with our substitution reactions, our SN1 and our SN2. Okay. So if we went through and looked at those, we could look at our mechanisms and try and see how that could help us. Well, in the case of the SN1, we saw two products come out of it. In the case of the SN2, we saw one product. So what we can do with our Diels-Alder reaction is we can now change the structure of our diene and dienophile such that when we run the reaction, we can look at the products and say, do I get one product or do I get two products? Okay. And depending on what mechanism and the results that come out of those necessary considerations for our mechanistic steps, we might be able to predict our products. Before we get too far into that, which I know is super exciting, you'll notice that we have that little p orbital floating out in there. Okay. What we're going to do is take a side step for the moment and look at molecular orbital theory. I know everybody's favorite. Okay. Remember, organic chemistry is all about the motion of electrons. All our atoms contain certain properties that allow the electrons to either stay or move depending on those situations. Electronegativity, for instance. So when we look at our atomic understanding of the atom, our electrons exist in an atom's electron orbitals, and we came up with the S, P, D, all of those fun things that you may have remembered from Gen Chem, if not from first semester organic. In a molecular understanding, those electrons now have to exist in a molecule's electron orbitals. They can no longer be atomic because the electrons aren't on an atom. They're being shared between atoms. So now our orbital discussion has to change. So there's a couple rules that come out of this. Number one, our molecular orbitals are made from atomic orbitals. And just like we learned in Gen Chem, we can't create or destroy matter. If we start with 4 atomic orbitals, we will end with 4 molecular orbitals. Okay? And it's just going to be some kind of combination of those orbitals. The next thing that's important to note is that all orbitals have phases associated with them. Okay? And that is typically shown as shaded or not shaded. Okay? The phases become relevant and will change when we pass through a node of where things or where electrons can't exist. So that when we look at the s orbital, there are no nodes within the s orbital. So our s orbital will either be entirely shaded or entirely empty. Our p orbitals, on the other hand, you'll notice that there is a node at the very center. That node is where our electrons cannot exist. So as we pass from our A node to our B node, the phase must change. So when we're looking at our molecular orbitals, one of those needs to be shaded, one of them is unshaded. Okay? So we always have these phases popping in. If we take a look at simple examples, say something like hydrogen, we take atom number 1 and we say it's hydrogen, and atom number 2 and we say it's hydrogen. We want to look at the potential for the molecule of H2. Okay, what's going to happen? Well, we're going to bring those atomic orbitals near each other and we're going to see how they interact. In that bottom circumstance, what's happening is those two orbitals were in phase with each other, which means when they overlapped, we had a constructive interference, and all the electron density now kind of sits between the two nuclei. In the top situation, our s orbitals were out of phase. Okay? Because every orbital has the possibility of being positive or in phase or out of phase. So what ends up happening is that when these things align, they don't interact, which means we get deconstructive interference, and now there is no likelihood of finding the electrons between the atoms. Just like with s orbitals, we can move this up to hybrid orbitals or even p orbitals, and we'd end up doing the exact same process. We look at the possible ways those two atomic orbitals can overlap. Do they overlap where they have a lot of electron density in between or no electron density in between? Okay, try to treat it as simply, as you can as that. So, what does that mean for us with our molecular orbitals for our Diels-Alder, which now looks massively more complicated? Okay, well, if we think back to our reaction, the electrons in this reaction are only coming from our pi system. We are taking pi electrons and we are rearranging those pi electrons into a new pi bond and to two new sigma bonds. Okay? So what we're concerned about is how many pi electrons there are and ultimately how many pi orbitals there are. Okay, so we're looking at one coming in from that carbon, one from that, one from that, one from that one. So we have 4 atomic p orbitals coming from our diene. From our Dienophile, we have 2 pi electrons coming in. If we're going to look now at our molecular orbitals, okay, well, for our diene, what we're doing is taking the atomic orbitals and we're looking at how the atomic orbitals can interact with each other. Okay, and in this case, what we want to do is pick the easiest one, typically the easiest one, is make all the orbitals overlap with each other so that we can get lowest energy conformation possible. Remember, we have to shade, so if I shade that one, the next orbital needs to be shaded in the exact same fashion. That way I can get orbital hopping back and forth through the pi system. I can move to the next one and the next one. That means an electron here can move potentially all the way around the pi system because all of those orbitals are now in phase. What we've now drawn is the lowest molecular orbital, or lowest energy molecular orbital. Okay? So what we would now do is repeat this process and each time add a node, okay, or a place that causes whoops. Not that big of a deal, but we'll include that. So I can shade these all the way across, and as you go through, you'll notice that we're going to start to see some differences pop up. Okay, and then our very last one, where they alternate all the way through. Okay, so for our very first or lowest energy molecular orbital, okay, you'll notice that all our orbitals are in sync with each other. Officially, we only have one node running through the plane of the molecule, okay, which I think looks confusing, so I'm going to get rid of that. Okay, so just one node. When we move up in energy, we have to increase the number of nodes, because that's what happens when we add nodes. We go up in energy. You'll notice we have another node right through here. An electron here can only jump to that orbital. It cannot make it to the next side because there's a node. We don't have the phases aligned to allow for that passage. When we move to the next highest energy, you'll notice that we actually have now 2 nodes. An electron here can't jump over there, but an electron here could jump to that one. When we get to the highest energy situation, we have 3 nodes. Okay? So we start with what I would actually call 0 to 1 to 2 to 3, showing all the increase in nodes as we move up in energy. Okay? Next part about thinking about this is then, where do our electrons exist? We've now drawn our molecular orbitals, so we have to put our electrons in. Well, how many electrons should we put into this? Well, hopefully you remember that we had 4 p orbitals, so we have 4 p electrons that need to go in. Where do we put our electron? Well, we'll start at our lowest energy first. Where do we put our next electron? We'll put our next electron in that exact same orbital, spinning the opposite direction. Okay, same deal as filling our atomic orbitals. We've now filled our molecular orbitals for the diene. We go through and do it for the Dienophile. I'll give you a second to pause and figure that out on your own. And we're back. We have 2 p orbitals from our Dienophile, which means I have 2 electrons that need to go in. There's my 2 electrons. Okay. For the course of this reaction to occur, we need to get these molecular orbitals to interact with each other. Okay? So between our, let's just start with our diene. In our diene, which of those molecular orbitals is most likely to interact with the other molecule? Okay, or with any molecule. If we're trying to form a bond, what do we need to have? Electrons. Where are the electrons? Only in the bottom two, which means the top two molecular orbitals are kind of irrelevant for us. What we need to do is look at those top two. Those bottom two. Between those bottom two, which one is most likely to share its electrons with something else? It should be the highest of those two, because it is now the highest energy, and our higher energy electrons are always more likely to react. Okay, so we've now found our orbital with the highest energy electrons. Kind of neat. This orbital happens to be referred to as our highest occupied molecular orbital, or our HOMO orbital. So it's occupied by electrons. Those electrons need to somehow react with our other molecule, which now brings in the next question. Which orbital would it most likely interact with? The top one or the bottom one? Okay. Hopefully you can come up with a reasonable guess that it needs to react with the top one. Why the top? Well, the bottom one already has 2 electrons. If we tried to mesh these 2 orbitals together, we'd end up with too many electrons in that orbital. So we have to react our HOMO with that top orbital option. Okay, well, that top orbital happens to be the lowest unoccupied molecular orbital, or our LUMO. So you'll hear reference to HOMO-LUMO interactions through this ultimate response. There's another little neat feature that comes out of this, which is the coloring system that we put into this. If we go through and look at the alignment of these, this orbital, if aligning from the bottom, could overlap with that, which would then mean this orbital would have to necessarily overlap with, oh my gosh, it is also unshaded. What's happening is that our HOMO and LUMO orbitals need to be able to overlap in such a way that we get that constructive interference that we saw, I'm going to regret doing this, that we saw all the way back here, so that we can put electrons between the nuclei. And if we scale this outwards to our final drawing, really what we're trying to do is to make sure that when we form those new sigma bonds, our sigma 2 and our sigma 1, that those orbitals are in phase with each other to allow for that interaction to occur. Kind of a neat process. We will talk about this more as the semester goes. We need to learn some more vocabulary before we push this too far. Okay. But now that we've got our orbital understanding of what needs to happen and that we're overlapping those orbitals, we can now look at kind of our reaction, our Diels-Alder reaction. So one of our repercussions of the alkene, which you may or may not remember from first semester, is that we have to be careful with our test reaction. What reaction are we going to use in lab to make sure we visualize this? And if we pick just the molecules that we ran with already, there's 2 possible orientations that those p orbitals can overlap on. Okay? So I'm referring to this as a sigma up because the sigma bond is aimed kind of upwards from our diene, or downwards, in the case of the sigma down, from our diene. This results in theoretically 2 different products. Okay, so what I tried to do was maintain these orientations, and I had to put in that little red marker. Okay, because if we don't have that little red marker with that extra carbon, there's no difference between those products. Okay, but as soon as we have that red marker, do we have a difference? What is the relationship between those molecules? Okay, and for simplicity, assume we lock the conformation so we can't change out of this now boat conformation. Hopefully what you see is that we get enantiomers. Well, this is going to become problematic for counting products because we're counting products, we're already starting out with 2 possible products, regardless of any other kind of orientations. Okay? So to simplify our mechanistic understanding, what we're going to have to do is just focus on, yes, we have a possible for enantiomers. Let's just see what happens by assuming one of those situations. When I go through the rest of these drawings, I'm now going to pick either the sigma up or the sigma down when I go through and draw, because I think one looks better than the other. Based on the drawings that I'm looking at, it looks like I'm going to pick the sigma down, but I don't remember, so let's take a look. Look at that. If we go through and work out our mechanism, we're going to look at the sigma down option, okay, and look at all our possibilities with that. With the DA1 mechanism, we said that we form sigma 1 first. So this is the formation of sigma 1. So we get our pi bond coming out, forming a new bond, a new sigma bond, and we're going to have to break the old pi bond. Okay? So this means our p orbitals are now overlapping in this fashion. If we go through and draw out this result, we now have the formation of sigma 1 in back. Whoops! Come back here. We have the formation of sigma 1 in back, and then we're still missing that space in front. All we're looking at is just kind of highlighting it. The interesting feature of this is because we're now in this conformation, this structure, or that bond, can freely rotate, which means A and B can exchange their locations. Why is that relevant? Well, if we look at the results, I now end up with these 2 possible situations. What's the relationship between these 2 products? Hopefully you can see that what we are looking at is diastereomers. Okay? So we're going to end up with 2 possible products related through diastereotopic relationships, which is nice because we can separate diastereomers away from each other. Okay, so if our DA1 mechanism, remember this is a guess, if our DA1 mechanism is correct, we end up with diastereotopic products, okay, on top of the enantiomeric products. So really when we look at the DA1 mechanism, we have 4 products coming out of this. That is a god-awful mess, so hopefully that's not the right answer. Okay, the other Diels-Alder type mechanism we could go through is in a DA2. And in the DA2, we said sigma 1 and sigma 2 were formed at the exact same instant. So when we're looking at our arrow pushing, everything happens at the exact same instant, and we are now automatically locked into this one conformation. There is no possible way to have A and C on the exact same side of that ring structure. Okay? So when we run the DA2 type mechanism, we expect really only officially 2 products because we have the enantiomer. Okay, so we're looking at 4 products versus 2. So what I kind of expect you to give a shot at with this is to grab a model kit and attempt to do this on your own to see what happens in each of these relationships. And if you do go through and use this model kit kind of idea that I'm showing down here, you will also see some necessary repercussions that happen to the substituents on our alkene, okay, which is going to be an important conclusion that comes out of our Diels-Alder that's more kind of relevant to our lecture. Okay? So please go through and attempt to do that. In our discussion, we were talking about simplifying things both for writing stuff up and for picking an appropriate molecule to react with. Okay? So you'll notice that in each of these kind of reactions, we're picking something really, really, really simple. Well, the really simple molecules then don't allow us to distinguish between enantiomers and diastereomers because everything's identical. So if we move to a slightly different situation, okay, where we can now identify our orientations. Okay, so what I've gone through and done is now used another diene, but this time it's a cyclic diene, and a Dienophile. Okay, So, and what we've done in this next situation is I've pulled both those structures kind of towards you, so they're coming out at you. And we're looking at this sigma up versus sigma down orientation. And what's kind of neat about this feature is that if we went through and did the sigma up, we'd end up with one product. If we did the sigma down, we'd end up with the other product. Okay? And this becomes problematic because this is our whole enantiomer versus diastereomer mess that we have to worry about. If you look at those orientations, our products that come out of this, because we've cyclized these, are now diastereomers, not enantiomers, which is kind of an interesting feature. Okay? If we push this further, we're also going to notice that the sigma up is going to have a very hard time reacting. Why might the sigma up structure have a hard time reacting? We've got this bridging atom that is now blocking the sigma up from happening. Why is this cool? Well, now instead of having the possibility of enantiomers coming out of our reaction, we end up with only one product. That's pretty freaking sweet. That has simplified our results. Okay, so by changing our structure around a little bit, we can prevent the formation of one of our reactions through a steric argument. So that'll simplify our isolation. So instead of seeing 2 and 4 products, we'll see 1 and 2, okay, depending on the mechanism, which is kind of a nice feature. But let's look at that again. Okay. You'll notice that in both cases, the sigma up and the sigma down, the oxygen on that ring is pointed the same direction. Does it have to be? I have 2 possible orientations for the dienophile. It could come in where it stacks underneath the diene, or it could come in where it stacks under but kind of away from the diene. That still produces that kind of or that diastereotopic product. Turns out that what we're looking at in this situation is an endo product versus an exo. Endo because what we've done has slid our diene underneath our dienophile underneath our diene. Exo because our diene is no longer underneath, it's kind of outside it. So if we look at kind of that box as a shelf, in our endo it's underneath, in the exo it's actually not underneath, it's out to the side of it. Okay, so we do have this added complication. We thought we could simplify it, and it just kind of creeps up on us and it says, heck no, you got to worry about it. Turns out that we can push this a little bit further. We don't actually have to worry about this. The endo product is the only one that is formed in Diels-Alder reactions. Okay, so we'd have to look at kind of our sterics on what's happening within this. In the case of the endo, it is a very sterically hindered product. Okay, we're taking these carbons and we're putting them very close to these carbons. That's a lot of steric hindrance. That's really bad, which what we would expect to happen is then greatly increase the energy of our product. Well, if the energy of our product is higher, it's very unlikely that's going to occur very quickly. In the exo case, we have this nice kind of steric spacing. Instead of being close to a 2-carbon bridge, it's a 1-carbon bridge. So the energy of our product in the exo should be lower, which would suggest we favor the exo. Okay. But it turns out that our primary driving force here is that our endo is favored because in the endo transition state, the p orbitals of those groups can interact with the p orbitals of our diene. We get a strong stabilizing interaction between those, which then lowers the energy of the transition state. So what ends up happening is we get a lower transition state. In the exo, there is no stabilizing feature. Our p orbitals are nowhere near each other for stabilization, which means its transition state is higher. So in the case of the endo, we have a low transition state. A low transition state means a faster reaction. In the exo situation, we have a low product energy, which means we have a more thermodynamically favored product. So we're looking at our kinetic versus thermodynamic products. Okay, kind of neat little stuff going on with that. Either way, we really only have to worry about that endo attack or one product being our primary situation, as long as we are using the cyclopentadiene as one of our starting materials, which we are. Okay. The next part of this is that what happens with this guy? What do we choose? Well, if we pick this molecule, we end up with how many possible products? 1, regardless of what mechanism happens. Why? Well, think about our two different mechanisms and what we said had to occur in the process of the reaction. Our primary difference was we needed rotation about that bond once the pi bond was broken. Currently, the pi bond wouldn't rotate. Okay, but let's say we get rid of that pi bond and we formed our first bond across. We end up with this transition state, and that's now a single bond. Can it rotate? No. Why not? Okay, so we want to change this starting material so that we can allow for rotation about that bond. If that bond can rotate, we now have the ability to decide which mechanism was more likely, the DA1 or our DA2, or maybe both. That'd even suck even more. Okay, so that's kind of what our lab is driving at, okay, as far as the chemistry goes. We're going to have all sorts of fun happening with calculations. You should look forward to that because it'll be exciting. Okay, so what we can do is push this a little bit further and move into the lab and see what the actual results are, but I'm going to hold it there, and I will reveal that information in a later lecture. For those of you not in the lab, I will announce when that next video is available, so you can go ahead and check it out and see kind of our overall summary of what happens with our Diels-Alder reaction. Is it DA1? Is it DA2? What a cliffhanger. We'll have to come back and see.